Welcome to this walkthrough of LeetCode problem number 1090, largest values from labels. In this problem, we'll explore how to select the most valuable subset of items while adhering to specific labeling constraints. Let's dive in and break it down step by step. In this problem, we are tasked with selecting a subset of items from two given arrays, values and labels. The array values represents the value of each item, while labels specifies the label associated with each item. On top of this, we are given two additional parameters, number wanted and use limit. Our goal is to choose a subset of items such that the size of the subset is at most number wanted, and we cannot pick more than use limit items with the same label. At the same time, we want to maximize the sum of the values of the selected items. What we need to return is the maximum possible sum we can achieve while satisfying all of these constraints. To clarify the output, we are expected to return a single integer that represents the maximum sum of the values from the subset we choose. Let's look at an example to better understand the problem. Suppose values is 5, 4, 3, 2, 1, and labels is 1, 1, 2, 2, 3. We are allowed to pick up to 3 items, as number wanted is 3, and we can pick at most 1 item per label because use limit is 1. The output in this case would be 9. This is because we can pick the items with values 5, 3, and 1, which correspond to labels 1, 2, and 3, respectively. Their sum, 5 plus 3 plus 1, gives us the maximum possible value of 9 under these constraints. Breaking down the reasoning further, the optimal subset in the first example is 5, 3, 1. To achieve this, we select the item with value 5 and label 1, the item with value 3 and label 2, and the item with value 1 and label 3. Adding these values together gives us a total of 9, and no other combination of items within the constraints of number wanted equals 3 and use limit equals 1 can achieve a higher sum. Now consider a second example. Here, values is 5, 4, 3, 2, 1, labels is 1, 3, 3, 3, 2, number wanted is still 3, but use limit is now 2. The output is 12, which we achieve by selecting the items with values 5, 4, and 3. These correspond to labels 1, 3, and 3, and their sum, 5 plus 4 plus 3, gives us the maximum value of 12. Looking more closely at the second example, the optimal subset here is 5, 4, 3. The item with value 5 and label 1 is selected first, followed by the items with values 4 and 3, both of which share the label 3. Since use limit allows us to pick up to 2 items with the same label, this selection is valid. Adding their values gives us a total of 12. Now, in a third example, values is 9, 8, 8, 7, 6, and labels is 0, 0, 0, 1, 1. Here, number wanted is 3 and use limit is 1. The output is 24, which we achieve by selecting the items with values 9, 8, and 7. These correspond to labels 0, 0, and 1, respectively, and their sum gives us the maximum value. In the third example, the optimal subset is 9, 8, 7. To satisfy the use limit of 1, we can only pick one item from label 0 and one item from label 1. Therefore, we select the item with value 9 and label 0, the item with value 8 and label 0, and the item with value 7 and label 1. The sum of their values is 9 plus 8 plus 7, which equals 24. This is the highest possible sum that meets the constraints. Finally, the problem includes some constraints and edge cases to consider. The array's values and labels can have up to 20,000 elements, and both the values and labels can range from 0 to 20,000. The constraints number wanted and use limit ensure that we carefully balance the selection of items to maximize the sum while adhering to the limits. Edge cases include situations where all items share the same label, where number wanted exceeds the total number of items, or where all values are equal, requiring additional focus on the labels and limits to determine the best solution. To solve the problem of selecting the largest values from labels while respecting constraints, we first consider the brute force approach. The idea here is to generate all possible subsets of items from the given array of values. For each subset, we check if it satisfies the constraints. The total number of items selected should not exceed number wanted, and the number of items per label should not exceed use limit. If a subset meets these conditions, we calculate its total value and track the maximum value among all valid subsets. However, this approach requires generating all possible subsets, which involves exponential complexity of O2 to the power of n, for a values array of size n. Additionally, verifying constraints and computing the value for each subset adds another O(n) per subset, making this method computationally infeasible for large input sizes. The brute force approach, while conceptually straightforward, is not practical for large datasets. With inputs as large as 10 to the power of 4 elements, the exponential time complexity renders this method unusable. To address this, we turn to a more efficient greedy strategy that focuses on maximizing the total value directly. The intuition behind the greedy approach is simple. Since we aim to maximize the sum of selected values, we prioritize items with higher values. To implement this, we first pair each item's value with its corresponding label, then sort these pairs in descending order of value. Once sorted, we iterate through the pairs, selecting items while ensuring that the constraints are respected. Specifically, we track the total number of items selected to ensure it doesn't exceed number wanted, and we also monitor the count of items per label to honor the use limit constraint. The process stops as soon as we've selected number wanted items or exhausted the available options. The greedy approach offers a significant improvement in efficiency. Sorting the items by value has a complexity of O(n*log n, while the subsequent iteration through the sorted list is linear, O(n). Together, the overall complexity is O(n*log n, which is much more scalable than the brute force solution. This method is efficient and straightforward, leveraging sorting to prioritize high-value items. However, it's important to note that while the greedy approach ensures optimality for this problem, it may not guarantee the best solution in scenarios with additional constraints. Despite this, the simplicity and speed of the greedy approach make it a strong candidate for this problem. An alternative to sorting is the heap-based approach, which achieves a similar goal through a different mechanism. The heap-based approach shares similarities with the greedy strategy but uses a max heap, or priority queue, to manage the selection of items. Instead of sorting all items beforehand, we build a max heap of value label pairs, allowing us to efficiently extract the highest value item at each step. This approach involves constructing the heap, which takes O(n), and iteratively extracting items, which incurs a cost of O(log n) per extraction. For n items, the overall complexity is O(n*log n), comparable to the sorting-based greedy method. However, maintaining a heap adds some implementation complexity. While efficient, this approach doesn't offer significant improvement over the sorting method for this particular problem, making it less favorable given the added complexity. The chosen strategy for this problem is the greedy approach with sorting. This method strikes the right balance between simplicity and efficiency. By sorting items in descending order of value, we align with the goal of maximizing the total value. During selection, we ensure that both number wanted and use limit constraints are respected, and the process stops as soon as the required number of items is selected. The time complexity of O(n*log n makes this approach scalable for large inputs, while its straightforward implementation ensures clarity. Key insights include the realization that sorting naturally prioritizes high-value items, and efficiently tracking the number of items per label ensures constraints are met without extensive overhead. While the heap-based approach offers similar complexity, its added implementation intricacy does not provide an advantage for this problem. The brute force approach, on the other hand, was dismissed due to its prohibitive exponential complexity. Overall, the greedy approach with sorting offers an optimal, practical, and scalable solution for this problem. The problem largest values from labels challenges us to select a subset of items that maximizes the sum of their values while adhering to two key constraints. First, we can select at most a specific number of items, determined by the number wanted parameter. Second, the use limit constraint ensures that no label is used more times than allowed. To tackle this, we use a greedy algorithm. The inputs include the values array, which represents the value of each item, and the labels array, which assigns a label to each item. Additionally, we have the number wanted and use limit integers to guide our selection process. The goal is to carefully navigate these constraints to achieve the highest possible sum of selected values. To begin solving this problem, we first combine the values and labels arrays into a list of tuples, where each tuple contains the value and its corresponding label. This allows us to work with the items as a unified structure. Next, we sort this list in descending order based on the item values. Sorting ensures that we always prioritize the items with the highest value, which is essential for maximizing the total sum. Once sorted, we set up the necessary data structures, a dictionary called label_count to track how many times each label is used, a variable total_value to store the cumulative value of selected items, and a counter selected_count to keep track of how many items have been chosen so far. Now, we iterate through the sorted list of items. For each item, we first check if we've already selected the maximum allowed number of items by comparing selected_count with number wanted. If we have, we stop further selection. Additionally, we check if the item's label has reached its usage limit by looking up the label_count dictionary. If the label's usage exceeds use limit, we skip the item. If both constraints are satisfied, we select the item by adding its value to total_value, incrementing selected_count by 1, and updating the label_count dictionary for the item's label. Once the iteration is complete, we return total_value, which represents the maximum sum of selected values while respecting all constraints. There are a few important insights that make this algorithm efficient. First, the greedy approach of sorting items by value ensures we always consider the most valuable items first, which is critical for maximizing the total. Second, the label_count dictionary provides an efficient way to enforce the use limit constraint for each label, allowing us to skip invalid items quickly. Finally, by breaking the loop early when selected_count reaches number wanted, we avoid unnecessary computations, improving the algorithm's performance. The algorithm relies on two key data structures: the list of tuples for sorting, which simplifies processing, and the dictionary for fast label usage tracking. Sorting takes O(n*log n), and the dictionary operations are O(1) on average, ensuring overall efficiency. Let's evaluate the complexity of this approach. The time complexity is dominated by sorting the items list, which requires O(n*log n). Iterating through the sorted list and performing dictionary operations adds a linear O(n) component, resulting in an overall time complexity of O(n*log n). For space complexity, we use O(n) to store the items list in OK for the label_count dictionary, where K is the number of unique labels. Thus, the total space complexity is O(n plus K). This makes the algorithm efficient and scalable for large inputs, provided the constraints are reasonable. When solving this problem, it's important to handle edge cases appropriately. For instance, if the values or labels arrays are empty, the result should be 0 since there are no items to select. If use limit is 0, no items can be selected, and the result is also 0. In cases where number wanted exceeds the total number of items, the algorithm simply selects all valid items without violating constraints. Another edge case involves duplicate values with different labels. The sorting step ensures that ties are handled consistently, and label constraints continue to be respected throughout the selection process. Let's walk through an example to see the algorithm in action. Suppose we have values equals 5, 4, 3, 2, 1, labels equals 1, 1, 2, 2, 3, number wanted equals 3, and use limit equals 1. First, we combine and sort the items into 5, 1, 4, 1, 3, 2, 2, 2, 1, 3. We initialize total_value, label_count, and selected_count to 0. The first item, 5, 1, is selected, updating total_value to 5 and label_count to 1, 1. The next item, 4, 1, is skipped because label 1 exceeds use limit. We then select 3, 2, updating total_value to 8 and label_count to 1, 1, 2, 1. Finally, we select 1, 3, bringing total_value to 9 and label_count to 1, 1, 2, 1, 3, 1. At this point, selected_count reaches number wanted, so the process stops. The algorithm correctly returns 9 as the maximum sum of selected values. This Python implementation solves the largest values from labels problem using a greedy approach. First, the values in labels are combined into a list of tuples, pairing each value with its corresponding label. Next, we sort this list in descending order based on the values to prioritize selecting items with the highest values. We use a label_count dictionary to track how many times each label has been used, ensuring we respect the use limit constraint. We also maintain a total variable to store the sum of selected values and number_selected to count the total number of items selected. The core loop iterates over the sorted items. For each item, we check if the label can still be used, i.e., its usage count is less than use limit, and whether we still need more items to meet the number wanted constraint. If both conditions are satisfied, we add the item's value to total, increment the number of selected items, and update the label's usage count in the dictionary. Finally, we include an early exit condition to stop the loop as soon as we've selected the required number of items, number wanted. This ensures efficiency by avoiding unnecessary iterations. The algorithm is efficient, with a time complexity dominated by the sorting step, which is O, n log n, where n is the number of items. The loop is O, n, making the overall complexity O, n log n. This implementation handles edge cases such as empty inputs, large use limits, or scenarios where number wanted exceeds the total number of items gracefully. Here, we start by importing the necessary Java utilities and defining our class and method. The goal of this method is to determine the largest possible sum of values from a given list, while adhering to constraints on the number of items we can select and the frequency of labels. First, we create a list of pairs, where each pair contains a value and its corresponding label. This helps us manage the association between values and labels easily. Next, we sort this list in descending order based on the values, ensuring that we prioritize higher value items during selection. The label count map is initialized to track how many times each label has been used, while the total variable will keep track of the sum of the selected values. There's also a number selected counter to monitor how many items have been selected so far. Then, we iterate through the sorted list of items. For each item, we extract its value and label, and we check whether selecting this item would respect both the use limit for its label and the number wanted constraint. If these conditions are satisfied, we add the value to the total, increment number selected, and update the count for the label in our map. Now, we include an additional check within the loop to determine if we've already selected enough items. If the number selected count reaches number wanted, we terminate the loop early, as there's no need to process further items. This optimization prevents unnecessary iterations and ensures the method runs efficiently. Finally, once the loop completes, we return the total, which now holds the largest sum of values we could select while adhering to the constraints. This approach ensures that we maximize the sum while respecting both the item count and label usage limits. To solve this problem, we start by pairing each value with its corresponding label, which gives us the list of items 5, 1, 4, 1, 3, 2, 2, 2, 1, 3. These items are then sorted by value in descending order, which in this case doesn't change their order. We initialize three variables, label_count, to track how many times each label has been used, total, to track the sum of selected values, and number_selected, to count how many items we've picked so far. Now, we iterate through the sorted items. The first item is 5, 1. Label 1 hasn't been used yet, and we haven't reached our selection limit of 3 items, so we select it. This updates total to 5, number_selected to 1, and label_count to 1, 1. Next, we encounter 4, 1, but label 1 has already been used once, which is the use limit, so we skip it. Then we process 3, 2. Label 2 isn't used and we can still select more items, so we pick it. Our total becomes 8, number_selected increases to 2, and label_count is updated to 1, 1, 2, 1. Moving on to 2, 2, label 2 has reached its use limit, so we skip it as well. Finally, we examine 1, 3. Label 3 isn't used, and we still haven't reached the maximum of 3 items, so we select this one. The total becomes 9, number_selected increases to 3, and label_count updates to 1, 1, 2, 1, 3, 1. At this point, we observe that we've selected 3 items, which is the exact number we wanted. Therefore, we can stop early without continuing further. The final result is the total value of the selected items, which is 9. Now, let's look at a different example where some labels are used multiple times. Here, the input consists of values 9, 8, 8, 7, 6, and labels 1, 1, 2, 2, 3, with number wanted set to 3 and use limit set to 2. For this input, we first pair the values and labels to get items equals 9, 1, 8, 1, 8, 2, 7, 2, 6, 3, and we sort them in descending order of value, which leaves the order unchanged. We initialize label underscore count as an empty dictionary, total as 0, and number underscore selected as 0. Starting the iteration, we process 9, 1. Label 1 is unused, and we can still select items, so we pick this one. The total becomes 9, number underscore selected becomes 1, and label underscore count updates to 1, 1. Next, we consider 8, 1. Label 1 has been used once, but the use limit is 2, so we can select this item as well. The total increases to 17, number underscore selected becomes 2, and label underscore count updates to 1, 2. Then, we examine 8, 2. Label 2 is unused, and we still haven't reached the selection limit of 3 items, so we pick this one. The total becomes 25, number underscore selected increases to 3, and label underscore count updates to 1, 2, 2, 1. After this, we encounter 7, 2, but since we've already selected 3 items, we skip it and stop early. The result is the total value of the selected items, which is 25. Now let's explore an example where there aren't enough items to meet the number wanted constraint. The input values are 10, 9, with labels 1, 2, number wanted is 5, and use limit is 1. First, we combine the values and labels into items equals 10, 1, 9, 2, and sort them in descending order of value, which again doesn't change the order. We initialize label underscore count as an empty dictionary, total as 0, and number underscore selected as 0. Processing the first item, 10, 1, we see that label 1 is unused, and we can still select items, so we select it. The total becomes 10, number underscore selected becomes 1, and label underscore count updates to 1, 1. Next, 4, 9, 2, label 2 is unused, and we can still select items, so we pick this one as well. The total increases to 19, number underscore selected becomes 2, and label underscore count updates to 1, 1, 2, 1. At this point, we've reached the end of the items, and while we wanted to select 5 items, there weren't enough available. The output is the total value of the selected items, which is 19. To analyze the time complexity of the largest values from labels problem, let's break down the major steps involved. First, we combine the values and labels into a list of tuples using the zip operation. This creates a new list of size n, where n is the number of elements in the input arrays. The time complexity of this operation is O, n, as each element is processed once. Next, we sort the list of tuples based on the values in descending order. This sorting step uses the timsort algorithm, which has a worst-case time complexity of O, n asterisk log n. Since sorting is computationally more expensive than the tuple creation, it dominates the overall time complexity so far. Once the list is sorted, we move on to iterating through it to select items. This involves a single loop that can run up to n iterations in the worst case. Within the loop, we use dictionary operations to track the count of labels. These operations, such as checking the count with label underscore count.get and updating the dictionary, are constant time operations on average. It's also worth noting that the loop may terminate early if the desired number of items, number wanted, is reached before processing all elements. However, in the worst case, the loop still contributes a time complexity of O, n. Combining this with the sorting step, the overall time complexity of the algorithm remains O, n asterisk log n. Now, looking at space complexity, the algorithm creates an additional list of tuples, items, which stores n tuples. This contributes O, n, to the space complexity. Another component contributing to space complexity is the label underscore count dictionary. This dictionary keeps track of how many times each label has been used. In the worst-case scenario, where all n elements have unique labels, the dictionary would require space for n entries, resulting in O, n, space complexity. Additionally, the sorting step with timsort uses temporary storage proportional to the size of the input, which also contributes O, n, to the space complexity. When we consider these factors together, the overall space complexity of the algorithm is O, n. Now, examining different scenarios, the best case occurs if the input is already sorted in descending order and number wanted is small, allowing the loop to terminate early. However, sorting still requires O, n asterisk log, n. In the average and worst cases, sorting dominates, and the time complexity remains O, n asterisk log, n. Comparing this optimized approach to a brute force method highlights its efficiency. A naive solution would involve generating all possible subsets of the values array, filtering subsets based on use limit and number wanted, and calculating the maximum sum. This approach has an exponential time complexity of O(2 to the power of n, which becomes infeasible for large inputs. On the other hand, the current solution uses sorting and a single pass through the list to achieve a much more efficient time complexity of O, n asterisk log, n, and space complexity of O, n. To mathematically verify the time complexity, we note that sorting contributes O, n asterisk log, n, and the loop adds O, n. Since O, n asterisk log, n, dominates O, n, the overall time complexity simplifies to O, n asterisk log, n. Similarly, the linear space requirements from the tuple list, dictionary, and sorting confirm the overall space complexity as O, n. When solving this problem, there are several common mistakes to watch out for. First, sorting the values array in descending order and directly picking the top number wanted items can lead to errors. This approach ignores the use limit constraint, which restricts how many items you can select per label. Instead, you should use a custom sorting approach or a priority queue that accounts for both the value of items and the label constraints. Another frequent issue is exceeding the use limit for a label. If you don't properly track how many items you've selected for each label, it's easy to violate this rule. The solution is to use a dictionary to count the occurrences of each label and ensure none exceed the limit. Additionally, some implementations fail to stop after selecting number wanted items, which wastes computation or produces incorrect outputs. To fix this, use a counter to keep track of how many items you've chosen and terminate the process once the limit is reached. Finally, tracking labels inefficiently, like checking or updating label counts in a list, can result in poor performance. A dictionary or hash map is a better choice since it provides constant time lookups and updates, making your solution more efficient. Another potential pitfall is misinterpreting the problem constraints. For example, some assume number wanted is a limit per label rather than a global limit, leading to entirely incorrect solutions. To avoid this, take extra time to carefully read and break down the problem requirements before starting your implementation. From an interview perspective, this problem tests your ability to balance greedy selection with constraint satisfaction, a classic hallmark of greedy algorithm problems. It's helpful to recognize that this is a variation of the knapsack problem, where the goal is to maximize the total value of selected items while adhering to multiple constraints. Highlighting this connection during an interview can demonstrate your ability to identify underlying patterns. Additionally, you should be prepared to discuss time complexity trade-offs. For instance, sorting the values array is often unavoidable and takes O, n log n, but efficient label tracking using a hash map ensures the overall solution remains performant. Be mindful of edge cases as well, such as when number wanted exceeds the total number of items or when use limit is set to 1, which imposes strict label limits. Bringing up these scenarios can showcase your thoroughness and attention to detail. This problem shares similarities with several other LeetCode problems, which can provide additional practice and insights. For example, LeetCode 1057, Campus Bikes, also involves greedy allocation under constraints. Another related problem is LeetCode 857, Minimum Cost to Hire K Workers, which combines greedy selection with specific rules for grouping. LeetCode 502, IPO, focuses on maximizing profits under constraints, often using a heap-based approach, while LeetCode 1288, Remove Covered Intervals, shares the need for careful sorting and condition checking. These problems are valuable for building intuition about constraint-based optimization. When it comes to alternative approaches for solving this problem, the greedy method with sorting is a common starting point. By sorting items in descending order of value and using a dictionary to track label counts, you can select items while ensuring all constraints are satisfied. This approach is straightforward and efficient, with a time complexity of O, n log n, due to sorting. However, it does require extra space for label tracking, so it's important to weigh these trade-offs during implementation. Using a priority queue is another effective strategy. With this approach, you dynamically pick the highest value item at each step while ensuring constraints are respected. This involves using a max heap to manage items and can be slightly more complex to implement than sorting, but it may save space in certain scenarios. On the other hand, a brute force approach involves generating all possible valid subsets of items and selecting the one with the maximum value. While this guarantees correctness, it's computationally expensive, with an exponential time complexity, making it impractical for large inputs. This approach is only viable for small datasets or as a theoretical exercise to confirm the correctness of other implementations. Each method has its own trade-offs, so understanding the problem's constraints and input size is key to choosing the best approach. Great job! To recap, we solved the largest values from labels problem using a greedy approach, sorting, and efficient data structures. This solution is both time-efficient and space-conscious. Remember to practice similar problems to sharpen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!